My slides are visible?
Yes, sir, it is visible.
Okay, perfect. Thank you so much. So good evening, everyone. Sorry for the delay. I was getting some connection issues. That's why I couldn't join. So welcome to the course of Fundamentals of Additive Manufacturing Technologies. Actually, there are three tutors for this course. One is on Friday, one is on Monday, and one is on Tuesday. So you can attend any one of these three tutorial sessions, because all these three tutorial sessions in a week will be the same. So for the next session, there will be one session on Friday and one on Monday and one on Tuesday. So there will be three different tutors, but they will be teaching the same thing, the same content of the course. But of course, there will be a difference in the teaching style and all. You can attend any of these three courses, any of these three sessions to get an idea of whom you are comfortable with. There is no restriction as to how many classes you do or what classes you do. So it's up to you, how you perceive it, and it's up to you which class to attend. So I will be repeating if some of you have joined the same session as on Friday. So I'll be repeating some of the sessions today as well. If you find it a repetition, maybe you can leave. Otherwise, if you find it a little bit interesting, then you can stay on. And tomorrow there will be another session. I think, yeah, 6 to 7, 6 to 8. It will be the same session, same repetition of the first 2 weeks. First week, sorry, first week 2 lectures. So there will be a different TA, and he will be teaching in a different manner, of course, but the content will remain the same. So it's up to you. Whenever you have a free time or whenever you are free, you can attend any of these three sessions. And this class is a 12 weeks course. So we'll be meeting each other for 12 long weeks, and we'll be considering some of the interesting concepts about IT manufacturing and IT manufacturing technologies. This is a purely fundamentals course, so mostly we'll be not going into much details about various technologies, but we'll be considering into the fundamentals of various technologies. So the course coordinator of this course is Professor Sajjan, and I am Vaibhav. Will be guiding you throughout the 12 weeks of this course. In my, as per my teaching process, what I will be doing, I'll be, because most of the concepts are covered by Professor Sajjan. So what I will be doing, I'll be taking you I will be repeating some of these contents, and I will be showing you some of the YouTube videos or the videos which I select, which I find interesting. So to give you a more descriptive or more informative idea or more application based idea about IT manufacturing, or why do we want to study this course? Why is this course necessary for us? So that will be my teaching style. And after that, I will be giving you some of the questions, which will in turn help you answer some of the questions of this week. But I will not give you answers directly, but I will be telling you how to approach the answer. And most of the questions, if you have any issues with these questions, we'll be discussing the answers of this week in the next week's content, because the answers will be released and the results will be out. So we can discuss those contents if you have some doubts. And if you have some doubts within the lecture, stop me immediately within the lecture. Do not keep it for the last. So if you have any doubts, stop me immediately. I will be able to answer this question. So let's begin the course. So the course is Fundamentals of IT Manufacturing Technologies, where we'll be getting introduced into IT manufacturing and various types of IT manufacturing, how IT manufacturing takes place, what are the applications of IT manufacturing, and why are we studying this course. To give you an introduction about IT manufacturing, most of these contents have been covered by Professor Surgeon, but still I want to go through to give you to recall you what are the definitions. So IT manufacturing, here AM refers to IT manufacturing. It's a set of technologies where we're fabricating a material in a layer by layer manner using a 3D model, as compared to as in contrast to subtractive manufacturing. What do you do in subtractive manufacturing? We take a material and we carve it out in the specified shape we want. But in case of IT manufacturing, what do? We take a material from, be it material powders or be it material wires or anything else, and then we directly frame those objects, directly carve out those objects without the use of any other techniques such as machining or wire EDM to cut the samples. We don't use that. We directly carve out the specimen in case of additive manufacturing. So due to this process, what benefits do we get? The benefits is that we can produce complex geometries. Just give me 1 second. We can produce complex geometries directly without the use of any of the machining techniques. Then mass customization, that is, we can customize the shape and the material as well in case of the additive manufacturing. Rapid prototyping, the process is pretty fast as compared to subtractive manufacturing techniques. Pretty fast in the sense, the machine, of course, the manufacturing time will be like 24 hours, 48 hours. If you consider it the pretty first term, it means that the post-processing techniques such as the machining and other things which we used to do in case of subtractive manufacturing, that is completely absent in case of additive manufacturing. And then design freedom. The shapes can be of any, the samples can be of any shape or sizes. It will be the additive manufacturing provides us the opportunity to fabricate that. Then the applications of there are various applications of additive manufacturing in various sectors, such as aerospace, automotive, medical implants, tooling, architectures, and variety of sectors. So I have 3 videos for you, which will give you a brief idea about additive manufacturing. What I said will give you a pictorial idea of how the world perceives additive manufacturing, and and there are some videos which will give you the applications of why you are studying this course or why this course is necessary for you to learn about additive manufacturing. So let's watch some of these videos. Just confirm that you are able to see the video and everything. Can I get a confirmation about that?
No, sir, it is not coming.
Okay, just give me 1 second. Okay. Now is it
Now
visible?
it is okay, sir.
Okay,
Yeah,
perfect. Great. Just give me 1 second. Just do not mind the ads you are hearing because I don't have a premium. So
अगर
will
आप
be
2,
just give me
3,
1
5
second
या
about the
उससे भी
ads.
ज़्यादा सालों से अपना बिजनेस चला रहे हैं और
Okay.
Now okay.
Additive manufacturing is a process where we take powder and turn it into parts. It is new, exciting technology that we're pursuing here in West Des Moines, and it's the future.
Really, the high-level definition of additive manufacturing is any process where a machine is working straight from some form of 3D geometry file to produce a geometry in a layer-by-layer fashion.
What makes it different from traditional manufacturing is rather than starting with material and removing what you don't need, instead you just add the parts that you need with different methods. You're basically building up a part with the material that you're using.
Additive manufacturing encompasses many different types of manufacturing processes. Here in West Des Moines, we actually use what they call powder bed fusion. That's where we take a large 3D printer, spread powder onto a build plate, and essentially use a laser welder to weld a 3-dimensional shape. It allows us to essentially take what a design engineer creates in a CAD model and print it from scratch.
Additive manufacturing has a lot of unique characteristics. And so as the manufacturing technology advances, we're going to be able to adapt a lot of aerospace product lines to include more additive. And it's really going to be integrated in the industry as a new method of manufacturing.
Additive really helps us reduce the lead time in what it takes traditional manufacturing. So a lot of the times we'll deal with a lot of castings. And if you have to change a tool or create a new casting, you could be looking at months to years in order to get hardware. Whereas additive manufacturing allows you to do it weeks or days, which all then allows you to say, hey, this didn't actually print correctly. Let's make these modifications and reprint.
So we started investing in additive technology about 10 years ago. We knew that it was going to be the future of Collins, that being able to design for additive and to be able to build parts additively was going to provide us great benefits, including cost reductions and faster time to market.
Additive here in West Des Moines means a lot of things. It means some opportunity for our designers to design new products in the future, really partner with our customers and start to, keep up with the new engines coming out. Along with that, for our operations teams, it means advancements in the operations capabilities to be more efficient and again, really start designing for the new engines that are out there and provide the right components to our customers that they're asking for.
We've got a fully functional, highly cross-functional team, engineers, operations, manufacturing here that enables us to do pretty much anything that Power and Controls wants. If there's something that you can think of that can fit in our build chamber, we can build it.
So this was just to give you an idea of where we are using additive manufacturing and how far in aerospace and various applications, as he mentioned in the video, like we are using additive manufacturing in various applications like aerospace parts, designs. And he said one statement that all the parts can be designed which will fit into the build chamber. So there is a build chamber which is necessary in terms of additive manufacturing. What is that chamber? We'll be discussing in further subsequent lectures. Just remember that as much as we can fit it in the build chamber, we can manufacture those parts. So let's watch the next video. It's also interesting in terms of that.
Additive manufacturing 3D printing है. किसी पार्ट को
Sorry.
Art or machining it, additive manufacturing involves technology that fuses the material, maybe using a laser in the case of metal, in order to build up the part one minute layer at a time. Because the part is built up instead of being machined from the outside or molded, additive manufacturing makes it possible to produce forms that maybe wouldn't be possible to make in any other way. Possibilities include parts that have complex internal channels, parts with lattice or honeycomb structures.
Just have a look at these structures, which is nearly impossible to break in case of casting, because these are tiny structures with pretty much precision in dimensions and details. So which is quite difficult to produce in casting and other subtractive manufacturing techniques. Whereas in case of additive manufacturing techniques, it's very easy to produce.
On the inside for weight savings. Additive manufacturing makes it possible to customize a part, changing the details at the last minute because there's no dedicated mold tooling. Also, additive manufacturing.
And the term mold tooling, he said, what does that mean? In case of casting, as you all know, in casting, what do? We prepare sand molding. In sand molding or any other casting, what do? We prepare the mold, we pour the metal into it, and the metal takes the shape of the mold, right? But there is a problem in that. In case there is a dimensional inaccuracy or there is a wrong mold, a wrong size of the mold, we cannot change it because we have to change the whole mold for that. But in case of additive manufacturing, if there is any error last minute, we can change. We can directly change the file. We can change everything, and the error can be avoided. So that dimensional accuracy and everything is good in additive manufacturing as compared to subtractive manufacturing.
Can eliminate a lot of assembly work because a part that might be assembled from a lot of smaller components could be grown as a single piece instead. Additive manufacturing makes a variety of end-use production parts, including jet engine components, other aircraft parts, medical devices, surgical implants. Additive is also used to make mold components that actually improve the molding process because the cooling channels, instead of being straight drilled holes, can be grown to conform to the shape of the mold surface. Additive manufacturing as a production option is still in its infancy. The number of users and applications is growing, but still small. Over time, additive manufacturing machines will become faster, their build envelopes will get bigger, the
Yes. So I told you one thing to remember about build envelopes or building chamber. Those are known as build envelopes. So that is a small limitation which we face in case of additive manufacturing. Why is that a limitation? We will be discussing in subsequent classes, but just to give you a brief idea why it's important. In case of additive manufacturing, so in case of powder bed fusion or in case of directed energy deposition, what we try to do, we try to avoid oxidation. We try to avoid oxidation because the thing is, laser is melting those, and if we melt those metal powders, while melting those metal powders, it comes in contact with the oxygen, it will oxidize and it will deteriorate the mechanical properties. So to prevent this oxidation, we create a chamber which is totally vacuum or argon spread. So while the chamber is vacuum and argon spread is the requirement of additive manufacturing for all the additive manufacturing or the powder bed fusion techniques. So to create that chamber, it requires vacuum as well as gas, right? Which is in turn increases the cost. So the size of the chamber is a challenge for additive manufacturing because we cannot go into infinite sizes of the chamber because the vacuum requirement will be high and the gas requirement will be high. So there is a restriction in the size of the chambers. Therefore, as the chamber size decreases, the part size decreases. So there is a restriction in the parts we can build. We cannot build a big airplane in case of additive manufacturing because it will require a lot of volume of the chamber. So that's what is the limitation what is trying to say. The build envelope size can be getting in future. We can develop something high powered vacuums or something which will develop a very big build chamber. But till now, the build chamber is a bit of limitation in case of additive manufacturing. Otherwise, rest assured, there are all positive things about additive manufacturing. Only the case is build chamber.
processing of various materials will be better understood. But the thing that'll really help additive manufacturing advance is designers becoming more aware of the freedoms and possibilities that additive manufacturing brings them. The established rules of what forms are manufacturable have, in a lot of ways, now changed. When people compare additive manufacturing and machining, what they forget is how capable modern machine tools are. A part that is machined effectively today probably will still be machined tomorrow. Additive manufacturing will replace machining for some parts, but the better way to think about additive is as a complementary process. One, because in metal, a part produced additively probably is still going to need finish machining. But also, two, because what additive really does is expand the range of designs that manufacturing is capable of producing. Additive manufacturing will be part of the future. How large a share of production additive manufacturing will account for is unknown. How quickly it will advance is unknown. But we will see additive manufacturing take its place as an established, accepted production option alongside molding, machining, and other processes. In the future, additive manufacturing will account for some significant share of the way that parts are made.
So this was about additive manufacturing, introduction to additive manufacturing, how the additive manufacturing, what is additive manufacturing and how the additive manufacturing is important in various industries. So let me take you through one more video about this introduction, where you will be getting an idea about the applications of additive manufacturing. Where are the various sectors? Brief application, like in the previous videos you got an application but it was specific, like okay, one side aerospace, one side okay, we are using in this industry, that industry. But in the third video you will be having an overall idea of what are the industries additive manufacturing goes into, plus what we will be getting an idea about how the additive manufacturing has developed from previously to today, how the additive manufacturing has developed. Let's watch the video.
Before 2020, the additive manufacturing industry experienced strong growth, averaging 27.4% year over year. But then the COVID-19 pandemic hit the world and global supply chains came to a standstill, making it difficult to meet production quotas. Manufacturing companies began to leverage the power of 3D printers to produce face shields, masks, nasal swabs, and ventilator parts. Artificial intelligence and machine learning also attracted mass attention, due in part that the engineering workforce has gone digital.
In this video, you will be seeing various types of additive manufacturing techniques as well. Some will be showing wire ADM, powder bed fusion. In the previous video, you saw about powder bed fusion, but here you will be seeing various types of techniques as well. Just have a brief, just keep in mind while you are watching the video, because we'll be going through the slide where we'll be discussing about various types of additive manufacturing techniques. But still, just watch through the video, and if you can get an idea of which is what, that will be helpful.
But how are artificial intelligence and machine learning key to additive manufacturing's future growth? What value can AI bring to the additive manufacturing supply chain, material development, machine perfection, part design, and workflow optimization? Find out now in Mechanical Engineering Magazine's special report. According to Wohler's Report 2021, the additive manufacturing industry grew despite the COVID-19 pandemic, expanding by 7.5%, nearly $12.8 billion in 2020. While the equipment sales saw a decline, the manufacturing of 3D printed parts rose dramatically to battle the pandemic and overcome supply chain disruption. The recent Additive Manufacturing Trend Report 2021 from 3D Hubs determined a 34% increase in engineering firms using 3D printing to produce functional end-use parts in 2020 compared to 2019. According to the report, the largest increase was seen in biotechnology, transportation, and automotive. GE has invested over $3 billion in additive manufacturing processes and uses it in many of its products, including jet engines, medical devices, and home appliance parts. The company's GE NX jet engine was manufactured using an advanced technique called direct metal laser melting. Boeing's Dreamliner 787 is the first commercial aircraft to fly using parts made with 3D printing technology, resulting in around $2 to $3 million savings per plane. 3D printing has become invaluable for manufacturers when producing on-demand spare parts, resulting in less operational downtime and significant cost savings. In February 2020, Etihad Airlines formed a partnership with the German mechanical engineering firm Big Rep to install their Edge 3D printer at its facility in Abu Dhabi. This made it possible to print both flying and non-flying parts on demand. 3D printing is shifting the manufacturing of expensive medical equipment to a lower cost point and with higher precision in the medical field. For example, the Open Hand project used AM technology to produce prosthetic hands for just $1,000, with the price of the units.
You see, previously we had an application in aerospace. Now we have an application in biomedical as well, prosthetic hands. So you see various types of applications as well. Just have a note to that as well.
Otherwise going up to $100,000. During the COVID-19 pandemic, HP partnered with the printing company Reddington 3D to produce.
You can also note the various companies, GE, Boeing, and HP. They are all parts of the using additive manufacturing technologies as well.
120,000 ventilator parts for medical equipment supplier Agva Healthcare in India. The partnership used AM processes to create ventilator parts such as inhale and exhale connectors, valve holders, oxygen nozzles, and solenoid mounts in just over 3 weeks, a process that typically requires 4 to 5 months.
If we say we want to reach into a level where machining, CNC machining is today, I guess to reach the full potential of the technology, I could imagine it will take at least a decade, maybe two. I think there's still a lot of potential. We are still in early stages, even though the technology exists for more than 2 decades. Well, if we talk again about powder bed fusion, there's a lot of room for potential in my point of view.
The cost of industrial machines for AM continues to be a challenge for even the largest of engineering companies. The average price for AM machines that produce metal parts ranges between $100,000 to $5 million. Material prices are also hampering AM adoption for high-volume production. Material costs can be 10 to 100 times more than a similar material for conventional manufacturing. While the scaling up of AM production has helped reduce material costs, it may take years for it to be on par with traditional manufacturing material. As new materials continue to become commercially available, the price of upscaling AM production will decline. Another hurdle is the evolution of 3D printing software. As 3D printing production started to mature, the gap between hardware and software became more apparent. Software is crucial in connecting all the steps throughout the AM process, from online ordering, part design, build preparation, production planning, and delivery. 2020 saw an increase in digital engineering as many were forced to work remotely. As a result, companies realized the investment needed in IoT and Industry 4.0 solutions. Many of the current AM software processes are inefficient and create production gaps. For both material costs and software processes, artificial intelligence can be a solution.
One of the most valuable positions or perspectives that I embrace is that AI technology is not confined by humans, but it really has the greater potential than humans or than biology to accomplish goals and to advance either industrial applications, healthcare applications, or material science opportunities, and be able to predict our world to do things or to understand things better, faster, and more concretely than we have before. So you have things that humans can do, but not as fast or proficient or accurately. And so using the tools that humans have made, including AI, in a way that's exponentially beneficial to return value and to accomplish goals that speed up, in my world, healthcare and the treatment of humans.
Generative design. The ability for computer-aided design programs to produce parts autonomously and organically has already seen increased adoption among part manufacturers. AI and machine learning can accelerate generative design and AM by designing parts free of traditional manufacturing restrictions.
When I think about AI, I think about machines improving their outcomes by analyzing real-world data much faster than humans could ever be able to achieve. And so those machines could be 3D bioprinters as well. And by leveraging the power of AI and ensuring that we can gather that data from 3D bioprinting, we can achieve those results of 3D bioprinting much faster than through human iterations on the printer itself.
AI can provide inspection benefits for AM systems in the hardware space to ensure greater process control and repeatability. AI can use pattern recognition to form best practices for error handling. AI-driven hardware can spot defects in part production and report it to the cloud. Workers on the line immediately pull the defective units before reaching final assembly, saving time and money in recalls and repairs. For example, Inkbit, an AM company based out of Massachusetts, is designing an AI-based vision system integrated into a polymer system to scan each of the 3D printing layers and predict material behavior during the print process. All in all, the use of artificial intelligence in additive manufacturing can cut the production time of 3D printed parts from 30 minutes to mere seconds per individual job. AI can increase printer utilization, optimize the material selection, reproduce production errors, and catch production defects along the way. Additive manufacturing today requires a high degree of specialized knowledge and highly trained engineers to be executed correctly. AI can help engineers ensure the rules of 3D printing are followed and help produce large amounts of data along the production process. By providing automated assistance, additive manufacturing enhanced by AI can be the manufacturing solution of the future.
Okay. So you got a whole idea about the different applications of additive manufacturing and the various kinds of additive manufacturing. If you got to see, because all the 7 additive manufacturing techniques were shown in this video, maybe you got 2 or 3. It's fine. We'll be looking at some other videos which will be giving you idea about the various additive manufacturing techniques in particular. So I think now you have a better idea about what additive manufacturing is, how additive manufacturing can progress in future, what are the what is the importance of this course and why we want to learn about additive manufacturing, and the various applications of additive manufacturing. So now let's just give me 1 second. Let me check if I've covered everything for this. Yeah. So now let's go into the steps in the additive manufacturing. This was also pretty much well covered in the lecture, but still I'll be giving you an idea about what are the steps. First, we go for modeling. That is done by you need to model your figures, like what geometry you are trying to produce by additive manufacturing, and to model that by using various AutoCAD or various SolidWorks softwares. Then you create that model, then you convert it into STL file. STL file is standard tessellation language, or standard. You know the form. You know the definition of STL, because there is a question regarding this as well in the week assignments. So yeah, standard tessellation language, which is like what is tessellation? Tessellation is tiling the surface with geometry without any gaps. Like properly like triangles are used for this, because this is the best figure which can give you a proper surface geometry of the figure, not having any gaps. Sorry. This is known as standard tessellation language, or STL file, which you are thinking about that. And this STL file has 3 vertices. As you know, triangle has 3 vertices and a unit vector which is normal to this plane. All this will be covered in further courses, and this was also covered in the second lecture as well, like the vertices and the unit vectors, how to find out, and we'll be also covering in this tutorial as we'll be solving some of the questions. Then after the STL conversion, we can do the manipulation. As I said, in additive manufacturing, we don't have a particular mold, which in case of which is present in case of the conventional manufacturing techniques. In STL, so we can manipulate the STL file till the end of the printing, or till we have started printing, or within like while going to the printing jobs. We can manipulate the STL file as well. Then the STL after everything is satisfied, you are happy with your STL file, we give it to the machine, provide to the machine where the machine setup is taking place. Machine setup includes variety of things. First is providing the STL file, which you are satisfied with. Then second, providing the powder, the starting material, that is powder or wire or anything you are giving, polymer, resins, anything you're giving, that's providing the starting material to the machine. Then with this, the machine starts and build your parts. Then there is part removal and cleanup. This is not considered as a post-processing technique, because you are building the part on a build plate and you need to remove those parts. Post-processing, in the sense, I'm talking about machining and other things, but this is not post-processing, because this is just the removing the parts from your build plates. Then if there is requirement of post-processing, this post-processing is what? Because there are some structures which are overhanging. Like, for example, you want a structure which is hanging out from the main part. So to create that structure, we cannot just directly load the STL file with the hanging in surface, right? Because you need a base. That hanging in structure needs a base. To create this base, we need support structures. This support structures removal is known as post-processing technique in additive manufacturing. This is not the same as the post-processing in conventional manufacturing where you are doing machining jobs. In case of post-processing in additive manufacturing, we are just removing the support structures, which are very easy to remove. Doesn't take much of time. Just hammer them out. Then it will be removed. Then after that, we can directly go for applications. After that, quality checks and other things, then we are going for applications. This is the whole step of all the additive manufacturing techniques. Like all the additive manufacturing techniques we will be learning follows this step, that is modeling, then STL file, STL manipulation, machine, it is provided in the machine, then goes to the build, parts are built, which are removed from the build parts, build plates, then post-processing, and then finally application. So this is the overall steps. And then coming to the types of additive manufacturing techniques, as I said, all these additive manufacturing, 7 additive manufacturing techniques follow the steps I have mentioned above in the previous slide. And there are 7, according to ASTM, there are 7 types of additive manufacturing techniques, and these are defined on the basis of energy distribution. But in this figure, I have in the lecture, Professor Sachin has mentioned according to the energy from starting from lower energy to higher energy. So starting from back polymerization to higher energy consumption, that is powder bed fusion and direct energy deposition. But in case of my slides, I have divided it on the basis of material processing, like what type of materials are being produced. On the basis of that, I have divided the categories, additive manufacturing categories. But if there is a question of dependent upon the energy, you have to follow the division or follow the categorization which Professor Sajan mentioned. So the on the basis of material processing, it is divided into 7 types as well. Binder jetting, starting with binder jetting, material extrusion, powder bed fusion, vat polymerization, direct energy deposition, material jetting, and sheet lamination. In binder jetting method, as the name suggests, there is a binder material and there are powder materials or any other polymer materials, and we're using the binder to fix or to join those materials. That is known as binder jetting method. Then material extrusion. In case of material extrusion, we are extruding a material up, and more details into this, I'll be showing you the videos. It will give you a brief idea about what I'm talking about. Just to give you an overview of what I'm talking about, I'm just telling you. Then we'll be watching those videos to give a detailed explanation about that. Then we have powder bed fusion, where you're using powder as well as laser to fuse those powders together to produce metallic pads. This is generally used for metals, powder bed fusion. Then we have vat polymerization. This has various subcategories as well. Stereolithography, continuous digital light processing, daylight polymer printing, digital light. And as you can see here, everything light is used. Here, the no use of laser. But here you will be seeing always laser, electron, they are used. Selective laser melting, selective laser sintering, multi-jet fusion, electron. These are all the terms which denotes that it requires higher energy. Powder bed fusion. That is, it uses laser to fuse those parts, because metal powders, these metal parts, they have temperatures ranging. For example, steel, they have melting points ranging at around 1000 to 100, 1000 to 2000, right? To melt those parts, we need a very high energy laser. That's why for fusion, it requires melting, and for melting, it requires high energy. So we are using laser here. But in case of vat polymerization, we are using a lower energy. So therefore, only polymers can be used in case of vat polymerization. That's why we are using daylight, digital light, only light is used in case of vat polymerization. Then we have direct energy deposition, which is also using a higher energy. As in case of powder bed fusion, both the energies are almost similar. But there is a huge difference between them. That's why we have categorized into 2 parts. Then we have material jetting and sheet lamination. As you can see, sheet lamination means we are using the lamination techniques to for the sheets. We are laminating the sheets in here. So let's watch some of these videos to give you a brief idea about what are the 7 techniques we are talking about.
Only
Sir,
6
is it
days
possible
master
to share
Vedic
the slides?
mathematics. Don't calculate.
Sorry? I
Is
couldn't
it
get you.
possible
Sorry.
to share your slides?
Yes, yes.
Is
I
it
will be sharing
possible
you
to
the
share your slides?
Yes, yes. I will be sharing my slides. Actually, you can go to the link. You can also see the link. There will be a I think in your NPTEL one, you will be seeing a link to all the slides and presentations. You can go there and all these lectures will be uploaded to YouTube, so you can go there and watch these lectures again, as well as you can access the slides and these videos as well. So don't worry about that. I will be sharing you the slides.
Okay, thank you, sir.
Additive manufacturing is one of the major advancements of Industry 4.0. It is comprised of several different processes using a variety of materials to create applications, with new production possibilities and solutions emerging as we speak. Each process follows 3 primary steps: design, slice, and print. A design can be created from an original concept, design,
So
slice,
this three,
and print.
this presentation shows that it has 3 things: design, slice, and printing. These things are divided into the processes which I have mentioned above. Design includes the STL file formation, then the SolidWorks or the AutoCAD design. Then slicing means the STL file manipulation and the STL file formation. This comes in the slicing. And then printing. Printing is providing the slicing, the STL file to the printer and then starting the print. So this is the whole overall technique.
Design can be created from an original concept utilizing computer-aided design software or CAD. By selecting an existing design through libraries or by scanning an existing part with 3D scanning. Each of these methods will then take the 3D model and create an STL file. The STL file is then transferred to slicing software, which preps the model for the final printing stage. The model is sliced into layers, and a path will be generated that the printer can understand. A variety of parameters can be adjusted during this stage. Manufacturing begins through one of the 3D printing processes. In each process, material is added layer by layer. In additive manufacturing, you're only using the materials that are needed, compared to some traditional manufacturing methods where the material is removed and scrapped. The materials utilized in additive manufacturing are vast, from metals to sand, and concrete to human tissue. Let's take a look at each process and which materials each supports.
Binder jetting printing process works by applying a liquid bonding agent to a powdered material. First, powdered material, either
So this is talking about binder jetting. What binder jetting does?
plastic, metal, glass, sand, or ceramic, is rolled out in a thin layer. The print head then applies the binder to the areas of the powdered material that will become the final part. The build platform is lowered, and the entire surface is recoated with fresh powder. This process is repeated again and again to build up parts layer by layer. After the printing process is complete, the loose powder is removed and a 3D printed part is extracted. Directed energy deposition, also known as DED, is essentially a form of build-up welding. The material, either in powder or wire form, is melted by an energy source while it's being deposited. The process repeats with each layer, adhering to the underlying layer. The energy source can be generated from a laser, electron beam, electron arc, or plasma. Directed energy deposition can make new parts, add features, or repair existing parts. Material extrusion works similar to a hot glue gun, where glue is heated and squeezed out as a liquid. For material extrusion, a filament or pellet material is heated and extruded through a nozzle and deposited onto a build platform, layer by layer. In more sophisticated systems, additional extruders can apply different materials within the same build, with one material acting as a support structure. The capabilities of material extrusion are diverse, ranging from consumer plastics to aerospace titanium. Material jetting uses a process and equipment similar to inkjet printing, but instead of dropping ink, the print head selectively deposits droplets of material onto the platform. An energy source, such as a UV light, is then used to cure the layer before dispensing the next layer. This process excels at producing parts and assemblies with excellent detail and a relatively smooth surface finish. Parts can be full color or have multiple types of material. Recent improvements in materials have led to its adoption for indirect and direct production of functional components. Powder bed fusion is a process where powder material is spread and a thermal energy source, such as a laser or electron beam, selectively fuses regions of the build area. The build box is lowered and the powder is recoated, continuing the process layer by layer. For polymer material, the powder surrounding the part acts as a support, enabling the production of complex shapes and fine details. Sheet lamination, just like its name indicates, is a process where sheets of material are stacked. The boundary of the layer is cut and bonded together to form an object. The sheet lamination process has many forms and can utilize a wide variety of materials, such as paper, polymers, and metals, along with numerous methods of bonding the layers of material. These bonding methods include adhesives, chemical, heat, and solid-state welding processes, such as ultrasonic consolidation. Vat photopolymerization gets its name from its original form of using a large vat of liquid photopolymer resin, or liquid plastic, which solidifies when exposed to a strong light source. The light source selectively cures a layer of the liquid material, and the platform and part moves together to let uncured material coat the next level. That polymerization is typically regarded to be the highest resolution AM process and is capable of producing parts with extraordinarily fine details.
These advanced manufacturing techniques are just scratching the surface of what's possible. Additive manufacturing is used to create prototypes and models. It's used in tooling, for repairs, and in the creation of end-usable parts. Just 30+ years young, additive manufacturing is still in the early stages of development. In Industry 4.0, what is constantly changing and evolving. So what's to come is beyond our imaginations. Or is it? Additive manufacturing has recalibrated what's possible in the minds of those who embrace it. We encourage you to explore projects here at America Makes. Maybe you'll be the next to create what will be. Thank you for visiting the nation's leading institute for the advancement of additive manufacturing.
Okay, so you got a brief idea about what are the different types of additive manufacturing. Now, for the next video, I want you to take notes, because in this video, you will be getting a idea about the advantages and disadvantages of various processes and a comparative study about the various processes and why is there a requirement of different types of processes. So for the next video, I really want you to take notes, like not exactly the notes, but some of the points you can note down, because it will give you a comparative understanding of various types of additive manufacturing techniques. So let's start the video.
You and I are not the same. This is how you treat your balls.
Sorry.
Types of additive manufacturing. These slides were developed by Rebecca Burton and Susan Arnold. The learning objectives for this module are to summarize the applied technology, the application to work and related work tasks, and build a process flow diagram linking work and work tasks to process, environment, and potential hazards. Additive manufacturing is broken into 7 categories. We'll take a closer look at each of the 7 categories, which include material extrusion, material jetting, binder jetting, powder bed fusion, directed energy deposition, vat photopolymerization, and sheet lamination. Material extrusion. In this technology, material is extruded through a nozzle or orifice onto the build platform. Like most AM, the product is built layer by layer. The feedstock for material extrusion is typically a solid filament, or pellets, composed of ABS or PLA. The polymer is heated to a temperature just above its glass transition temperature and extruded onto the platform. Fused deposition modeling is a trademarked variation of material extrusion that generally refers.
So the material extrusion is known by a different name as well. So do not get confused if someone says that, okay, there is a different process names or you find different names anywhere. Do not get confused, because sometimes material extrusion is also called fused deposition modeling. So do not get confused about that.
Modeling is a trademarked variation of
What do you
material
mean by
extrusion
PLA,
that
sir?
generally.
Sorry?
PLA.
Can you repeat the question?
Definition PLA. What
I'm
do you
sorry, can
mean
you?
by PLA?
Okay,
Can you
PLA.
hear me? What do you mean by PLA?
It's a different way. You can search for that. It's a different category of polymer. So yeah, these are the ABS and PLA. These are the
ABS,
different types of polymer which you can manufacture through material extrusion. These are examples of polymer. You can have a look into that. You can just type it in the Google and look into that. What are they? Yeah.
Transition temperature and extruded onto the platform. Fused deposition modeling is a trademarked variation of material extrusion that generally refers to industry-scale machines that are equipped with enclosed heated build chambers. Fused filament fabrication is similar to fused deposition modeling, except fused filament fabrication generally refers to lower-cost desktop material extrusion printers. Tissue models constructed from cells using fused filament fabrication support medical research, pharmaceutical drug delivery, among other applications. Material extrusion major steps. The major process steps related to potential exposure to health hazards are pre-printing, during which polymer filaments or pellets are loaded into the printer, post-printing, during which the machine is open to retrieve parts, and post-processing, during which parts are polished using acetone vapor or chloroform vapor. Material extrusion materials. Feedstock material.
So now you got an idea what PLA and ABS is. ABS is acetonitrile butadiene styrene. This is PLA is polyacetic acid. These are all the different varieties of polymers.
Materials used in material extrusion include acrylonitrile butadiene styrene, polylactic acid, acetone, or chloroform. These materials have the potential to evaporate when heated, and the contaminated air could be inhaled if the worker is exposed to it. Other hazards include hot surfaces, nip, pinch, or puncture of skin when interacting with the printer, and potential exposure to VOCs resulting from thermal degradation of the filament. With material jetting, hundreds of...
So you got an idea about what material extrusion is, what are the hazards and what are the disadvantages of that as well. So now we are going to a different technique, that is material jetting. Let's see.
Micronozzles are used to extrude a liquid resin onto a build platform. Dissolvable support materials, including waxes, gels, and wax polymer blends, are used in the printing. The resin is selectively cured using a UV laser. This process is repeated, building a product layer by layer. Major process steps related to potential exposure to health hazards include pre-printing, when the resin is loaded into containers, post-printing, when the part is removed from the build platform, and post-processing, when the parts are submerged into the batch to be washed. Materials used for material jetting include resins that are selected to impart specific colors and performance characteristics, such as flexibility and surface appearance, dissolvable support materials including waxes, gels, and wax polymer blends. Other hazards include UV radiation, thermal degradation products, surface contamination with resins, inks, support materials, and nip, pinch, puncture points. Binder jetting is a method wherein a liquid binder
So this is the third process, binder jetting.
is selectively applied in the pattern of a layer of a product and then cured or sintered. Binder jetting is comprised of a powder reservoir and a build platform. The major process steps related to potential exposure to health hazards during pre-printing, the powders are loaded into the printer. A roller rolls a layer of powder from the reservoir onto the build platform, and the printhead applies one layer of binder, and then the binder is initially set by having an infrared lamp array pass over the top. The building platform then lowers, the level of powder in the reservoir is raised up, and the process repeats until all layers have been printed. This produces a green part, the part made of powder fused together with binder, submerged in a bed of unfused powder. This is an important feature of the method because it doesn't require any support materials to be integrated into the design, which is necessary for some other methods. During post-printing, the green part, in its box of powder, is placed in an oven, usually overnight, where the application of heat cures the binder enough that the green part can be handled without breaking. Next, it has to be removed from the bed of loose powder. This is usually done by digging the part out with a spoon or spatula of some kind, and then the harvest part is cleaned by having the loose powder blown off. This can be done in a glove box, something like a fume hood or a downdraft table, or simply out in the open, depending on the particle size of the loose powder. After that, the green part is generally sintered in a furnace to remove the binder and fuse the powder material into a finished part.
Yeah, so did you get what it said? Because in this case, the binder is not essential. The binder is only essential to fuse those layers, right? So the binder is not essential, and the binder, as you know, can be evaporated or can be removed if we heat up to a certain temperature. The binder can be removed. So that's what it is trying to say. As the binder is not necessary, and the importance of binder is just to fuse those parts, and the binder has fused them. So the binder at the later stage, what you are doing, we are heating up the sample to remove those binders.
Size of the loose powder. After that, the green part is generally sintered in a furnace.
Yes, the green part is generally sintered. Sintering means we are not melting the part. We are just heating it to a certain amount of temperature, which is way below the melting point of the material. So just to remove the binder.
To remove the binder and fuse the powder material into a finished part. Sometimes the voids created by elimination of the binder are backfilled with a secondary material, such as bronze. This is done post-processing. Feedstock materials for binder jetting include metal powders, mineral powders, binders, and cleaners. Powders, binder vapors that have evaporated from the heated binder or from cleaners, can be inhaled if the worker is exposed to the contaminated air. There is also the potential for dermal exposure from contact with surfaces that are contaminated with metal powders, binders, or cleaning agents. Other hazards associated with binder jetting include exposure to hot surfaces. This technology includes two main types of processes: selective laser melting and
Yes. So the powder bed fusion is in turn divided into two things, which is selective laser melting and one is electron beam melting. As you see from the name, there are two different things. One has a laser in it, and one has an electron beam in it. So that means in selective laser melting, we are using the lasers to melt those materials, as I told you earlier. And in electron beam melting, we're using electron beam to melt those materials. In both the techniques are same. Like one is using, we are using metal powder, we are melting the metal powders to fuse them together. But the process of melting happens in very different types. In the first way, we are using laser, and the second, you are using electron beam.
electron beam melting. For selective laser melting, a blade is used to spread a thin layer of powder across the platform that is then melted by reflecting.
The whole process stays the same. Only the difference is the power supply. One is using laser and the other is using electron beam.
A laser beam using a mirror. The process is repeated with the fresh layer of powder building the part layer by layer. Electron beam melting is, as the name suggests, an application in which the electron beam is used to melt the powder. This causes less residual stress compared to the electron beam melting, with less distortion, and as a result, the need for anchors and support structures is reduced. With this technology, the environment in the build chamber and AM machine must be blended.
So you understood a difference, like why we went for electron beam melting, right? Because the stresses, residual stresses, which are generated in case of selective laser melting is quite high. And if this residual stresses are present in case of your final products or final application parts, this will create a huge amount of deterioration in the mechanical properties, because as the residual stresses develop, there will be stresses applied, environmental stresses which is applied on the sample, and this will create cracks in the material. So to overcome that, we're going for electron beam melting.
Blanketed with an inert gas to prevent feedstock powder oxidation. Major process steps related to environment in the build chamber.
So you can see here, I told you about the build chamber as well, right? The build chamber is created to prevent oxidation. We are creating a build chamber which is either vacuum or in case of selective laser melting, we are using argon gas. But in case of electron beam melting, we cannot use gas. Can you tell me a reason why we cannot use gas in case of electron beam melting? Has anybody, can anyone give a guess?
Because a vacuum we have to generate we should have a big chamber and a vacuum pumps is a mandatory. Argon if you add it, inlet if you give it is kind of full. So we cannot generate a vacuum if you are inserting argon.
No, you are right, but the question is why electron beam uses vacuum and why selective laser melting uses argon? Because the two processes are different. You know the difference? Yeah.
Electron. If we are not generating a vacuum, electrons will be decelerated. It may not be focused in a one single point. For that, vacuum is a mandatory.
Perfect. That's the answer I wanted. So in case of gases, because the argon gases, they are very heavy gases, laser will not be deflected. As she said, laser will not be deflected. But in case of electron beam, the mean free path of the electrons is necessary for the melting. Because that's how we know the electron is focused. So if we add gases into the chamber, the mean free path will be deflected and the electrons will be deflected, and there will be a less amount of melting because the electrons are deflected and the concentration of energy will be less. That's the reason we are using vacuum in case of electron beam, and in case of laser melting, we are using argon gas.
An AM
One more
machine must be
clarification.
blanketed with
You told
Yeah.
You told laser melting the residual stresses are more compared to EB welding like that.
Yeah.
But the thing is, electron beam welding is a low heat input process. Okay, compared to LBW. In that, when we are giving lower heat input, so the melting also will be sufficient only. That time residual stresses will be less for EB welding compared to less for LBW compared to EB welding. No?
No. So the thing is, the difference is when we're using a selective laser melting, we're using this residual stresses really depends on the process of melting, how the melting takes place. In case of laser, it is more concentrated and multiple. What is the reason of residual stresses generation? Because in case of laser melting, multiple layers are.
I
Sorry,
got it
go ahead.
now. Okay.
Okay.
I got it now. Laser beam means instead of 1.5. In EB welding, we can go for 3 mm thick. In laser, we can go for 1.5. So 2 times we are increasing the heat input. So when we are increasing the heat input, accordingly, residual stresses also will increase.
Yes.
Okay, I got it.
Yes.
Thank you.
Okay.
Inert gas to prevent feedstock powder oxidation. Major process steps related to potential exposure to health hazards associated with powder bed fusion include pre-printing, post-printing, and post-processing. During pre-printing, powders are weighed, mixed, and loaded into the printer. During post-printing, the printer doors are opened so that the part can be retrieved and depowdered. During post-printing, the printed part is cut away from the build platform and grinded to produce the final product. Materials used in powder bed fusion include metal powders, plastic powders, and powder blends. There is potential inhalation exposure to the powders that have become airborne. Similarly, powders that have settled on surfaces that a worker touches could lead to dermal exposure. Other hazards include hot surfaces, ionizing radiation, and pinch nip punctures. Directed energy deposition uses focused thermal energy produced by a laser or electron beam to fuse melted materials as they are deposited. The material is a metal powder or wire. This process produces near-net shape parts, meaning that the parts produced are very close to the desired final shape and size. This technique is attractive for its ability to reduce production costs and time associated with finishing steps. Unlike the other AM processes, with DED, multiple materials can be deposited simultaneously so that functionally graded parts can be made. Because of the 4 or 5 axis motion system that positions the deposition head, the process is not limited to horizontal layers, making it possible to repair existing parts. This process is also well suited to making large metal parts. Major process steps related to potential exposure to health hazards associated with directed energy deposition include pre-printing, during which wire or powders are loaded into the printer, post-printing, when doors are open so that the parts can be retrieved, and when the parts are cut away from the build platform. Finally, during post-processing, parts are machined to achieve final part dimensions. Major materials used in directed energy deposition include metal powders and metal wire. The use of ionizing and non-ionizing radiation sources also represent potential exposure risks. The use of nitrogen for creating an inert environment can also present an oxygen displacement risk. With vat photopolymerization, a solution of photosensitive monomers is exposed to a light source at the surface to cure those materials into a final object. The material undergoes a photochemical reaction, polymerizing it into a solid. In the case of photopolymerization printing, depending on the materials within the resin, you can get flexible, intricate parts or more ridged parts depending on the level of the plasticizer present in the solution. Once the UV light cures the part, there is excess resin left over in the vat, and the build tank or platform moves to accommodate building of the part layer by layer. The scope of types of parts that can be formed in photopolymerization printing is vast, and in fact many of the techniques used can create very small intricate parts, depending on the size of laser or light source. Major processing steps related to potential exposure to health hazards include pre-printing, when resins are mixed and dispensed into the vat, during post-printing, when the printer doors are opened to retrieve the part and cure it with UV radiation, and post-printing, during which the part is sanded and drilled. Materials used in vat photopolymerization include photopolymer resins, solvents, pigments or dyes, and other additives needed to achieve the desired product characteristics. These materials can evaporate and expose the worker via inhalation and contaminate work surfaces, leading to potential dermal exposure. Other hazards associated with vat photopolymerization include non-ionizing radiation. Sheet lamination materials include metal foil, polymer films, paper, and adhesive. Other hazards include non-ionizing radiation and ultrasonic noise.
So this was all about the different categories of additive manufacturing, and you got a detailed idea of how they are different from each other, what kind of difference, and how the subclasses are different from each other. So yeah, now we got an idea about that as well. Let me just have a look if I've covered everything regarding that. Yes, we covered that. Okay, so next, yes. So in the week, in the same week, we had a lecture two about there are a variety of techniques like how we are ASCII techniques, binary, then binary techniques, and the solid modeling techniques like CSG, B-RAPE, FBM, SD. And I will not go into much detail about that because Professor Sajjan has given you a brief idea about what is required, and I would not go deep into that. But of course, we'll be solving some questions related to that. So yeah, let's start with the questions. Okay. So in this, so it will be a great help if you can answer some of the questions in the chat box so that because these questions have options in it. So if you can answer these questions in the chat box, then it will be helpful. I will be giving you 10 minutes to answer all of these 4 questions in the chat box. You can mention them as question 1, 2, 3, 4, or anything, whatever you like. Prava, can you look at your first and your fourth answer? Can you just read it again? First and your fourth
The
answer.
tools and the fixtures used in additive manufacturing process are dash the object geometry.
Yeah.
It's I have what I have to do.
Like, is it dependent, independent, similar,
I have
opposite?
written as a I have I have written as a dependent.
Yeah. So is it? Are you sure it's dependent to the object geometry? Just think again.
Is it,
You can take your time. We have not started discussing yet.
okay. It's independent.
We have not started discussing yet. I'm just waiting for other answers as well. So it's a you can discuss
Okay.
your answer. We can discuss it later. You can just keep your answers to yourself.
Okay.
Because I saw some of the answers, they are correct, and some of the answers which are slightly incorrect. So I'm just trying you to think again. I'm just telling you to think again.
Okay.
And your fourth,
Actually, why I
and your
have to
fourth
put the
answer
dependent is
sorry.
why I have put is a dependent is today I am making one shape, tomorrow I am making another shape. According to the different shapes, we have to make a tools and the fixtures. That basis I have to put dependent on an individual object like that.
Okay, so what are the tools and the fixtures you are using in additive manufacturing? That is the
Tools,
trick in the
for
question.
example,
What that is the trick in the question. What are the tools and fixtures used in the additive manufacturing? There the answers rise. Do not confuse it with the subtractive manufacturing such as mold. What are the tools and
understood.
fixtures used in additive manufacturing?
Okay, okay.
Just think about that, then you can get the answer. Joshua, can you look at your, can you just think about your last answer once more? Last answer. Okay, now you can start discussing. Give me 2 minutes. Slides are visible? My slides are visible? Hello?
Yes, sir, it is visible.
Okay, perfect. So the tools and fixtures, just a second. The tools and fixtures in the item. What are the tools and fixtures? Can somebody answer me? What are the tools and fixtures used in the item manufacturing? What are the tools and fixtures? What are the tools and fixtures used in additive manufacturing? Because the tools and fixtures used in subtractive manufacturing are what? Mold, then shovel and anything else you are using for sand molding, injection molding. You know what are they? But what are the tools and fixtures for additive manufacturing?
Sir, is the laser, UV rays.
Perfect. Great answer. Do you think anything else?
Like build plate.
Sorry?
Build plate.
Yes.
The bed, print bed.
Perfect. Great answers. So these are the textures, BUILD, build plates. So these are the these are the fixtures and the tools used in item manufacturing. Does the laser and the build plate change while we are changing the object geometry? Yes or no?
No, sir.
No.
Exactly.
No.
Exactly. So the laser and the build plate doesn't change, right? That means the tools and fixtures are independent to the object geometry. We don't care about what the object geometry is, because the laser has a mirror which can rotate in all the directions, which can create the parts. It doesn't care about what the object geometry is. That's the answer. Prabha, did you get it?
Yes, sir, I got it.
Perfect. Okay, I think the second question, most of your answers are correct, so I will not discuss it in much detail because you understood what the question was. The support is used to realize the overhanging structures. As I mentioned, as professor also mentioned, and I also mentioned in the presentation, an identification of the region required, the support is carried out at the identification is required in the pre-processing stage, because in the post-processing you cannot do the identification, because post-processing only the removal of the structures is carried out, and the pre-processing this identification of the region is carried out. So overhanging and pre-processing, and most of your answers are correct, so I'm quite happy about that. Then this question,
Sir, your slide is not visible.
Sorry, slide is not visible.
Slide is not visible.
Okay, just a minute. Let me try once again. Okay, just give me 1 second. Just give me 1 second. Okay, now is it visible?
Yes, sir, now visible.
Perfect. Great. So just give me 1 second. Okay. This question, I think most of them are correct, but I will discuss this once again. As per the occurrence of AIM processes, put the following operations in right order. What do you think? The preparation of STL file should be the first option, right? We have to prepare the STL file. This should be 2. 2
Yes.
should be 1. Then what we will be doing? We'll be doing the STL file manipulation.
Manipulation.
We'll be manipulating the STL file. I will be preparing the STL file. Then we'll be using the slicing software to manipulate the STL file. Then after manipulation, we'll be doing the support structure. Here, some people I think have mentioned this as the last one, but we'll be generating the support structure after that. Because before slicing it, we have to generate the support structure, because the support structure will be sliced. What do you mean by slicing? Slicing means it will be directly fed to the machine. And in slicing, it will be all broken down into triangles. This is the last process. So the support structures also need to be broken down into triangles before they can be processed. So 2, preparation, then STL manipulation, then generation of the support structures. After every manipulation, you have to support structure is the last process in case of manipulation. Then finally, we'll be doing the slicing. That is 2, 3, 1, 4. Finally, we'll be doing the slicing, and after slicing, we'll be sending it to the software, sending it to the machine. So the process will be 2, 3, 1, 4. Okay. The next question, I think very less number of people got it correct. I think 2 or 3 were correct. So the answer will be boundary representation, BREP. This is the model. All these processes are discussed in case of the presentation. Can you give me a brief idea about all these processes? Can someone tell me about CSG? What does this process mean? What is CSG process and what does it mean? A brief idea, just one line answer. Can someone tell me?
So CSG or a constructive solid geometry is basically where we draw the sketch and we use the specific command to create that model, like constructing it step by step.
Okay. So the thing is, to give you, your answer is good, but to give you a better answer, what we do, we suppose we have two things, like this is a cylinder. We have one cylinder, and within that there is a hole in this. So this is the solid geometry we are trying to prepare. So in CSG model, what we do, we have to prepare a bigger cylinder first. We have to give the dimensions to prepare a bigger cylinder. Then we have to prepare the smaller cylinder. We have to prepare the smaller cylinder. These are the two solids we are preparing, because that's why it is known as a solid geometry. We are preparing two solids and then we are integrating it. So how will be integrating? We'll be putting this solid inside this solid. Then it will give you a full overall this solid. So that is known as a constructive solid geometry. We are using two solids to construct the geometry. So known as constructive solid geometry. Then let's come to feature-based modeling. What does feature-based modeling mean? FBM.
So like the features we use in CAD software, using that we create the model.
Perfect. Perfect answer. So we are using features. Like, what are the features which are necessary? Features. Like, for example, the same cylinder we are taking, the same cylinder. Then we have a hollow cylinder. This is the hollow cylinder. What we are trying to do, if anyone has any experience on in solid modeling or in SolidWorks, what do we do? How to manufacture this? We'll be manufacturing a circle, and within that we'll be manufacturing another circle. We'll be doing this. Then we'll be extruding, right? If somebody has used SolidWorks before, SolidWorks uses feature-based modeling. We'll be extruding it according to this height. We'll be giving this height and we'll be extruding it. This is known as feature-based modeling. We'll be giving the features to the material and then we'll be extruding it. That is what he was also trying to say. Sorry, who was it who gave the answer? Sorry, I couldn't get your name.
Joshua.
Oh, thank you so much, Joshua. Okay, next, space decomposition. Will give me an idea about that. SD. It's a very interesting one.
So it's a collection of tiny cubes representing the model, like voxel.
Perfect answer. So the tiny cubes, as he said, are known as voxels. So what we'll be doing, let's take the same geometry. We're taking a hollow cylinder. What we're doing, this portion which has material, this hollow cylinder, this is the portion which doesn't have material, forget about that. The portion which has material will be divided into small cubes. These small cubes are known as voxels. And these small cubes are put together to generate this process, to generate this model. That is known as space decomposition. The difference in between in triangles and cubes is that the cubes is a three-dimensional model, right? That's why it is known as a space model, space decomposition, space. But in STL, what we are doing, we're using triangles, right? So this is not in a space, it's in a surface, right? Did you get it? It's a surface because triangle is represented on a plane, not in a space. That's the difference between space decomposition and STL. That's the difference between space decomposition and boundary representation. We discussed everything, but in STL, what we are doing, as we know, we are dividing the whole figure into triangles. And these triangles have three coordinates or three vertex and a normal to it. This is the feature of boundary representation. In three triangles, we are defining three vertices, right? These three vertices are the boundaries. There comes the term boundary representation. Now you can relate how you are getting the answer. Everything has answers in its name. Constructive solid, feature based, space, cubes, feature, extrusion, and then we need the features. Constructive solid, we need two solids and then we join together. In boundary, we need triangles and we need give the boundary conditions. That is what STL format is. Boundary representation, BREP. Is everyone clear? Yes or no?
Yes, sir.
Perfect.
Yes, sir. Yes, sir.
Thank you so much. Okay, then we have three questions. The last question is a theoretical question. It can be answered very easily. But the second two questions are like mathematical questions. These are not heavy mathematical questions as well, because some of the examples are being solved in the presentation by professor as well. So yes, if you can give me the answer to these two questions, you have 10 minutes. Remember, before solving the first question, you have to check if the triangle is formed or not.
Excuse me.
Yeah. Does anyone have any question? I think people are finding it difficult, is it? Shall I help you with the answers?
Yes, sir.
Yes, sir.
Okay, perfect. No worries. So can you just tell me how to know if three coordinates are in the straight line or form a triangle? Can you tell me how to know that? So these are the 3 points, x1, y1, z1, x2, y2, z2, and x3, y3, z3. So these 3 points will form a triangle. Can you tell me how to know that? If it forms a triangle or not? No idea? Yes or no? Yes or no? Okay, I'm assuming you have no idea. That's why you're not answering. Okay, fine, no worries. So, okay, 3 point. You have been given 3 points. That has like three coordinate, 3 points, 2, 2, 0, and this. So these 3 coordinate points will form a triangle that we can confirm. So to form a triangle, all these 3 points should not be collinear, or at least one of these points should not be collinear, right? If 2 points are collinear and one of the all the 3 points are collinear, it will be a straight line. No triangles will be formed. But at least one of the point is not collinear, then we can form a triangle, right? So the requirement is that
Yes.
the points should not be collinear. And how can we relate collinearity to determinant? If the points are collinear, the determinant must be 0. Then the points are collinear. So how to know that this forms a triangle? We have to find the determinant of these 3 coordinates. So how to find the determinant? 2, 2, 0, 2, 4, 2, and minus 4, 4, and minus 2. To find the determinant of this, you will find the answer. The determinant will be minus 40. That means these 3 points are not collinear, are non-collinear points. That means this form a triangle. Therefore, you can get the equation of the plane in the vector. How can you get that? Let's suppose the equation, the plane has the coordinates of x, y, and z. Then how can you know the coordinate? How can we know what is the equation of the plane?
చేసేస్తానమ్మా కోర్స్ ఏదో ఉంది చూస్తా
Doesn't even know. How can we know the answer? How can we find the coordinates of the plane? We just need the equation. We can find out. You can refer to the formula which is used in the lecture courses. You can go back to the lecture and see how the question is solved. This will help you in solving the question as well. So x minus x1, these are x1, y1, and z1. x2, y2, and z2. x3, y3, and z3. So x minus 2, y minus 2, y minus 2, and z minus 0. Then x2 minus x1, 2 minus 2, 0, 4 minus 2, 2, 2 minus 0, 2. Then x3 minus x2, minus 4 minus 2, minus 6. 4 minus 4, 0. And minus 2 minus 2, minus 4. You have to take the determinant of this equal to 0. And then you can find the value of x, y, and z. This is how you solve. Why is it happening and where I got these equations from? You can go back to the lecture once again to get an idea, because the professor has also solved the exact similar question. So then you can get an equation in terms of x, y, and z. So that will be your answer. Then in this question, so in the lecture there was a session on like the deviation tolerances, and in case of deviation angle tolerances and all these things. You can go and have a look of how these questions are being solved. What is deviation tolerance? What is angle tolerance? Then we can solve this question. Maybe we will try this question once again next class after you have solved these two questions, after you have gone through the lectures once. Can you answer me the last question? Let's leave this for the next class. Next class. Can you solve the last question? This will be the last question for the day, then we can discuss. Can you answer me the last question quickly? I'll give you no time to solve this question. Just answer me this question.
How many triangles required for deviation tolerance to be 0.005 now to represent a circle?
You can leave this question. You can leave this question. I want to
A
answer
circle
you.
of
I want you to answer the last
radius.
question. The last question. The vertex in the STL file can be shared by dash number of triangles, and the edges can be shared by dash number of triangles. So this is the triangle I'm drawing you. This one is the vertex. This can be shared by how many triangles? And this is the edge. And this can be shared by how many triangles?
Six.
6? Which one is 6?
There were 6 triangles.
Okay. Okay, let me tell you the answer. This answer will be 2. This answer will be infinite. So this is the vertex. This vertex can be shared by infinite number of triangles. You can do as many number of triangles in this. If you decrease the size, it will fit. If I draw a bigger triangle, this will fit maximum of 4 or 5. But if I decrease the size of the triangle, infinite triangles can be formed. So this vertex can be shared by infinite number of triangles. But the edge can only be shared by 2 triangles. You see, I can draw one more triangle, not more than that. This edge, I can just do one more triangle. So this edge can be shared by maximum of 2 triangles. But the vertex can be shared by infinite number of triangles. That was the answer to this question. Okay, so this question we'll be solving it in the next class. I will be repeating this question in the next class as well. So yeah, if you have no doubts, we can disperse for today. Thank you so much for attending. And all these lectures you can find on YouTube as well. I'll be uploading it to YouTube. If you want a repeat of this lecture, you can go to YouTube as well. I'll be uploading it by tonight or maybe tomorrow. Thank you so much for attending.
Thank you, sir.
Thank you. Thank you.
Thank you.
Thank you.
Thank you.
Thank you, sir. Thank you.
Thank you. Thank you, Jayashree. Thank you. Good night. Thank you.